Expert with us this week, Michelle Alim, and she is a Northwestern girl. She grew up in Renton. Okay, so many of you guys joining us hopefully are from the Northwest. And she went to the University of Washington and got a degree in aeronautics and astronautics. And she's worked at Boeing, right? So Washington Company, and now she is at JPL. And the reason why we asked her here today, and by the way, JPL stands for the Jet Propulsion Laboratory, which is in California. Are you in California currently?
Yes.
Okay, I know that a lot of people are working remotely, so. But the reason why we asked her here today is she's at JPL and she's actually doing flight software engineering for the Europa Clipper mission. So they're developing that mission, getting ready to fly, and there's lots of design and testing to do on the back end. So you guys heard from a scientist the last time we did a meet an expert, but I'm sure as Michelle can tell you, like most of the people that work on missions are actually engineers. There's more engineers than scientists because it takes a lot of engineers to make the mission happen and the science happen basically. So I will go ahead and hand it over to her and let her get started.
Awesome. Thank you, Darcy. Hi, everyone. As mentioned, my name is Michelle, and I am working right now on the Europa Clipper mission at the Jet Propulsion Lab. Quick disclaimer before I get started, I'm not here representing NASA or JPL or Caltech, so everything I say is just my own views. But that said, I'm really excited to talk to you all about what I do and more importantly, how I kind of got here. I was super excited when I heard that I was going to be able to talk to you all because I took a look at some of the roads on Icy World, like material online, and it just seems like such a fun, cool project, really cool setup and so detailed. And it's really similar to the process that, we go through on our project where we have these mission objectives and then you're working in teams and documenting what you're doing, et cetera. So I think that you're already really getting a taste of what real scientists and engineers are out there doing on big missions with this project. So I think there's going to be hopefully a lot for us to talk about. So that said, feel free to interrupt at any time with any questions. I can't guarantee that I'll be able to answer all of them or maybe even any of them. I don't know how tough our questions will be, but I'll try my best. And if you don't want to unmute, feel free to just throw your question in the chat and I'll try to make sure I keep an eye on that as well. So as mentioned, I am a Northwest native. I grew up in the Renton area. And Renton is really, or at least it felt like, the heart of Boeing. So aerospace was kind of all around growing up. A lot of my friends' parents used to work at Boeing in various engineering and mechanic type roles. And I actually wasn't born in Renton. I was born abroad in Pakistan. So every few years we would fly these super long flights to go visit my grandparents and my family that was still there. And when you are on a plane for 24 hours straight, you start thinking about the airplane you're in because there's not much else to do. And that's kind of where I started between, the influence in the city I grew up and then those trips every couple of years. I really started getting an interest in airplanes. I just thought they were incredible, that they were able to connect people. I thought it was amazing that we could go so far in these man-made machines. So I always kind of had an interest in that and kind of related because aerospace kind of comes under one umbrella. My dad was always really into astronomy and planetary science. And so I always had a bit of that influence as well. And, you think about going far, well, across the globe is one thing, but going across the solar system, that's incredible. So that seemed a little bit more of a far-fetched dream at the time. So I never even considered it as a possibility, but life takes you places you don't expect. So I grew up in Renton and ended up going to University of Washington in the Seattle area, really close to Renton. And they have a fantastic aeronautics and astronautics department, which I knew kind of right away I wanted to join. And it was a really fantastic experience for me as a student, not just because of the classwork, but also because of all of the different projects that I got to do. And I happened to be able to get a tour my first day there of the wind tunnel. And that ended up being basically life-changing. And I'm curious, does anybody here know what a wind tunnel is? No pressure, because I didn't until the tour I took when I was in college. So a wind tunnel is kind of exactly what it sounds like. There's basically a physical like room, that's the, I guess, tunnel part. And there's some big fans. In our case at UW, there's two. And the fans, you turn them on and there's wind and it's really fast. Now the UW one was subsonic, so it's like considered a low speed wind tunnel. But the reason that that's really important is because as much as we know about flight and as much as we know about some of the forces and some of the science of what happens when something takes flight, there's a lot we really don't know. And wind tunnels help in especially early design phases to learn about those. And rather than having to build a whole like airplane every time you want to make some design change, you can make a small scale model, put it in the wind tunnel, turn on these huge fans and start testing it out. So that was a really unique job because it's very hands-on. It was something that you don't just get in the classroom. So similar to hopefully the projects you're doing, it's not just like reading in a textbook and then, okay, answering some questions on a piece of paper. It was a hands-on job. So our customers were actually real engineers, real companies, not just other students. And we were, as students working at the wind tunnel, helping them do, their experiments and doing everything from helping them change the hardware out to taking all of this data that we collected. So the wind tunnel basically collects data like the forces that are acting on whatever you're testing. So whatever you want to see, let's say like your aircraft model, for example, and it does a lot of processing of the information, post-processing of the information collected, and that is naturally done by a computer. So when I started working at the wind tunnel, I found myself sitting in front of the computer a lot and programming, and I didn't even know that that's what I was doing because I was not formally introduced to that. But when you have, it's sort of when you have a separate project that you're interested in or you want to do, and to be able to do it, you have to like teach yourself a new skill. That's kind of where I was at. And so through college, I found myself at work and both for my classes as well, sitting in front of the computer, writing code. And, unbeknownst to me, I was teaching myself how to program. Through some connections I made at the wind tunnel, I was able to get an internship and then eventually a full-time job at Boeing. And when I got there, I kind of told, early on to one of my mentors that, oh, I really like, this coding thing. I think it's super fun. And they were like, oh, we need people who like that and are good at that. And they started assigning me a lot of projects where I would have to be developing a lot of code. So I was formally an aerodynamics engineer, which made sense because my degree was in, aeronautics and astronautics, but I was doing a lot of programming. And so I started to delve more into that topic. So I want to take a quick pause here to point something out in the story, which is the importance of really good mentors. I don't think there's anybody in really any job that they like who hasn't gotten there without a really impactful mentor. And I know certainly for me, I've had a lot of different types of mentors who have helped me get to like the next job I want, or just helping me with the current job, helping me with, things totally unrelated to work. So if you find someone that you just click with, don't be afraid to ask them like, hey, can I stay in touch with you? I would love if you could be my mentor. And maybe they'll be your mentor for, a couple of months and help you out in your specific project, and then you'll part ways. And maybe you'll really click and you'll be mentors for multiple years. So the mentor that I'm mentioning, who I was at my first job, she and I have actually stayed in touch, even though it's been like many years since we've worked together in any formal capacity. So that was a little side note, but really, really want to stress the value of like making those important personal relationships as well. So as I was getting these programming assignments at work, I was reading so much more online about programming, and I kind of one day was sitting there with, myself and two other aerodynamics engineers, and I sort of looked around, and we were all like sitting on our computers. We were working on this code for a tool that we were making that was like analyzing basically damage to aircraft, and we were like, all programming, and I realized there was like a room of 6 aerodynamics engineers that were all trying to program, and none of us had like formal programming background. We all knew how to do it, and we could certainly throw together a script if we had to, and we could, you know, Google and find the right things and copy paste and make the little tweaks, which is a lot of what programming is. But I realized that there was like a cool like niche that I could potentially fill, which is I know how to talk to these like aerospace engineers. I know how to talk their language, at least a little bit, because I've kind of gone to school for that. I've been around that for at least a few years. But I don't really know how to talk to the people who could help us improve our code, right? I don't have that computer science vocabulary. And I realized that to be a better aerospace engineer, if I learned computer science, I could be, you know, a much stronger aerospace engineer, because that's something I happened to like already. So I decided to go back to school because that's the way I prefer to learn. There's lots of different ways to teach yourself that skill. And I decided, you know, going back to school, that formal path would be really good for me. So I decided to go to graduate school in California and got my master's in computer science, always with the goal to stay in aerospace. And when I came to Southern California, I realized like, oh, JPL, Jet Propulsion Lab is here. And I never thought of, you know, NASA or JPL as something that I could truly achieve, because it just, you know, wasn't, sometimes you miss what's not obviously right in front of you. But there would be a couple of like career fairs at my school, and I would see folks from there, and I would always be like, oh, this would be, you know, this would be really cool. And the nice thing about aerospace is that they don't tell you, that I only learned when I was in college, is you can bounce between the aero and astro side. You know, it's not like you pick one path and then you're set. It's not like, oh, you're going to start working on aircraft to work on aircraft forever. You can, those skills are very transferable, and people tend to like both. So I'm a big advocate for like explore the whole aerospace industry if that's what you're interested in. And that's what I ended up doing. So I got my computer science degree and then eventually ended up at JPL, where I now am working on the Europa Clipper project. So I've been here for about 3 years, and I've been working on the software for that. I started working a little bit on software processes and basically kind of making sure, you know, a good process creates good product, basically, is kind of a philosophy that they have. And so I started off working on making sure that those processes were really clean. And now I'm working on the actual product. So now I'm working on flight software, and we'll get kind of into the details of that in a bit. But that's sort of my high level school to career journey. So any questions so far? I'll take a little break.
Let's see if we can give them a minute.
Sure.
Here we go. Can you see the chat, or do you want me to read it out?
Nope, I got it. So the first question here says, what language do you use for scripting, out of curiosity? It really depends. That's a really good question. So at the wind tunnel, we used a lot of MATLAB. In my classes, I would use a lot of MATLAB, some Python. And then, you know, at work, it's really dependent on the project. The kind of biggest split is between ground software and flight software. So ground software is exactly what it sounds like. It's software that's running for basically everything on the ground that's then going to communicate with everything on the spacecraft, which is the flight software. The flight software is all written in C because it's embedded software and it has a lot of like performance requirements. The ground software, you can basically have fun and kind of, you know, whatever's the cool new technology that people are trying and they want to mess around with. So the ground software is a lot more of like a Frankenstein. You have a lot of programs that are in Python, especially now. A lot of things are converting to Python, but you still have a lot of stuff that's like written in C. I would say those are kind of the main ones that I've seen so far, though. Another question we've got is there anything you were involved with in high school or wish you had been that would have benefited you now as an engineer? In high school specifically, let me think. There wasn't a ton of engineering type clubs at my school, which in retrospect, I wish I had just started. And that's something I'll also plug here. If there's something you want to do and it's not at your school, go find a nice teacher, tell them to be your advisor and start it. I did do a couple of like business and speech related clubs that I actually think have helped a lot, because there's a lot of communication involved in engineering because it's a team sport. And so I actually think those benefited more than I thought they would. How much time did it take to learn coding and to master it? Ooh, I don't consider myself a master at all. And I'll tell you why, because coding is a totally evolving skill. So I might become like a really strong coder for the project I'm working on right now. But the next project might have a totally different like set of requirements, a totally different architecture, a totally different goal. And those things all drive the type of programming you're going to be doing. So not just necessarily like what language you're using, even because you might be using Python on all three projects, but they might be very different like applications. They might be very different infrastructures that you're using. And a lot of what you do as a programmer is like, oh gosh, well, why is my computer not starting up today, right? There's all of this like infrastructural stuff that goes with it. And you kind of have to like get the kinks out of the system, and that's a big part of it. And to the other end of that question, there's always new things coming out, right? Like there's things that, there's new technologies that you want to be able to leverage. Now with space specifically, it's a unique challenge because we have to make sure that we use technologies that are like tried and tested. So really anything that's like flying is probably 10 years old, right? Like it's something that we know has worked, because you don't have the same type of risk tolerance versus, something like ground software. As I said, again, you can kind of have a little more fun. With that said, we do try to like use new technologies and bring those into our processes a lot of times. So just a year ago, I started getting a lot more familiar with like Elasticsearch, and that was super new and I'd never seen before. So it's definitely something where you have to keep your skills kind of sharp and up to date, because there's so many new things coming all the time. A Python question. How much of the Python C code uses in-house libraries, frameworks versus open source libraries? We have a lot of in-house frameworks and libraries. So basically, the very high level architecture that I'll say for our mission specifically is there's basically, and this is going to be pretty specific to like my job. We are doing what's called flight software integration testing. So what I'm responsible for is there's the flight software that, as I mentioned, is the software that's running on the computer that's on the spacecraft, right? So if you consider if you consider the spacecraft, you can kind of think of the computer that's on the spacecraft as the brain of the spacecraft. And we're basically writing the code for that computer. And then we're also testing that code for the computer. But there's two levels of testing that code. So there's the code that the developer, so the same person who writes the code, tests, and that's called unit testing. And what they're basically doing, because the way that the flight software is created is there's basically like hundreds of little modules, and they each have their own little thing. So you can kind of think of it as if you have your personal computer at home, you've got like a program that's like for word processing, like Word, and you've got your Excel, and you've got your PowerPoint. Those you can kind of think of as kind of analogous to the various modules. So you have one person working on Word, one person working on creating PowerPoint, etc. But it's obviously for spacecraft, so it's more like one person working on propulsion and one person working on guidance and control, etc. And they write the code for that. And then they kind of test it, assuming nothing else in the world exists. It's just their perfect little PowerPoint module that they're working on. But the reality is that that actually lives in the broader context, right? It's not like you can just pull their module out of thin air and that's it. What you really have to do is you have to go and power on your computer. Then you have to make sure that your file system works so you can go find the application icon and then double click it. And then you can use, their wonderful PowerPoint program that they created. So what my team does is that process of turning the computer on and then finding the program where it lives, and then double clicking their buttons and making sure, oh, you said that I could add a picture. Can I actually add a picture? And oh no, I found a bug. I can't resize this picture. That's what integration testing is. So to get back to your question of what in-house libraries and frameworks we use a lot of custom libraries to do the things in that process that are repeated. So, and those will transfer from mission to mission as well. So, you know, a lot of what we do is inherited from like the Mars missions, the other like large missions that have come before us, and then they build on top of that, which is not to say we don't use a lot of open source stuff as well. We absolutely do. But there's so many things that are so custom to the flight software that and ground software that we're working on. That was a really long answer for a simple question about frameworks, but it's a very exciting system, and I can talk about it in great detail if you'd like. Are unit tests strictly written by developer who implemented the tested code, or by someone else who is designated specifically for unit tests? Great question. In our workflow, generally the person who writes the module writes the unit test for the module. So, and then they have an assigned integration tester for that module. So for example, my kind of areas that I overview are like instrument managers. So there's one flight software developer who writes the flight software for instrument management for these 7 different science instruments that Europa Clipper has. And then they write the unit tests for them. And then I test all of their modules, but in that integrated picture that we talked about. And I often have to refer to their unit test because sometimes there might be something that I can't test that can only be covered by a unit test. So a lot of the other people are definitely reading and reviewing their unit test, but generally nobody else is writing it. What would you say is the hardest thing you have had to learn in programming? Ooh, that's a really good question. I think one of the things that for me has been very challenging that I'm still kind of wrapping my head around is the unique performance requirements, because that's something very particular to embedded software, which is what flight software is. You know, if you pull out your cell phone and you click on, you know, your Instagram app or whatever, and let's say it takes like a few minutes longer or like a few seconds longer, right, than usual to load, that's super annoying, but it's not the end of the world. Your phone isn't going to break. Nothing's going to happen. If you miss timing requirements on something like Europa Clipper, you might have wasted like millions and millions of dollars and years of travel because, you know, you don't get the same type of flexibility. So that's been something very interesting to learn about, is how are they optimizing this very, the software within this very, very specific hardware as well. Another thing that I think is really unique to flight software that I'm enjoying learning about, and that I think is quite challenging, is fault protection. So, you know, again, because these are such large, certainly in the case of Europa, expensive, you know, flagship missions that we really, really want to succeed, right? Like, there's a lot of redundancy. So you actually don't just have one computer in the spacecraft, you have like 2 computers, so that if one fails, the other one can pick right up where the first one kind of, you know, died or whatever happened to it. But making that a smooth transition is very tricky, because it's not just like, oh, we'll just turn the power off on that one and the power on this one. It's like you have to find exactly what broke and then make sure that all of the information is transitioned smoothly, that you don't lose any information, right? We certainly don't want to go from, you know, after 6 years of travel time and get to Jupiter, get to Europa, and then find out we lost half the data because there was some glitch and something happened. So I think that fault protection is a really unique challenge, because it takes a lot of software skills, but it also pulls from a lot of other disciplines. What would you say is the hardest thing you have ever had to learn in programming? Ooh, that's a good question. Let me think about that one. I think there's a lot of really hard things. Everything feels like the hardest thing when it's the bug right in front of you. So I'll put it that way. I think the hardest thing I've learned is actually that sometimes you have to step away from the code sometimes to figure out what's going on. It's very tempting when you're working super late at night and you're just like in the thick of it and you think your code is about to work, and then you know, hit enter and oh gosh, you hit this bug, and then you're staring at it for hours and hours and hours figuring out what's going on. And sometimes it's actually really good Just step away from your computer, go take a walk, go have a snack, and you'll come back and you'll be like, oh, all I did was just have to move this one variable. So yeah, sometimes I have to relearn that lesson every time I have a tricky bug. Somebody says rubber duck debugging is my favorite way for figuring out bugs or just things. Absolutely. So for those who aren't familiar with the term, rubber duck debugging is, it's basically like, picture that you have to explain your code or your problem to a rubber duck. And it's just the process of talking through it to this inanimate object can sometimes help you realize as you're explaining what's going on. So absolutely, I definitely second using the rubber duck method. All right.
That's funny. I've never heard of that. I want to ask you one more question though.
Absolutely.
As we're talking, because I was thinking about the testing, and then I was also thinking about, the two computers. So I guess my question is, like, do most of the test engineers that work during the development end up working during the mission? Because you guys are potentially, like, if you think about something in the mission breaking, like, the only way you can fix it is by uploading new software. So you guys are kind of like the heroes that can save a mission if something goes wrong.
Yes, so, I mean, you can think of it as the hero, but also as the culprit who probably messed up in the first place. Right?
I don't know. I feel like the hardware people always mess up, but that's
well, and that actually brings a really, really good point, which is with these space missions, you can't change the hardware. You can change the software. So it's I don't want to say easy, but it's easier to then just go ahead and update the software. So exactly as Darcy said, oftentimes during the mission, like during operations, so that is to say once the mission has launched and the development stage is over and it's sort of handed over to the folks who will actually be using all of that software that's been developed, there will be anomalies. There will be things that happen that weren't supposed to. And it depends on how they end up approaching it. So sometimes there are people who will be on the development team and then will transition to the operations team. But it's typically, it's not like the whole development team will go to the operations side. You might have one or two people and they might just do it because they really like that project or they want the experience. But generally people tend to prefer one or the other for whatever reason. But let's say that something does happen in operations and there is some issue. And so the operations folks try to see, what's going on, and they write up and they dig around, and then they might not be able to figure out because maybe they don't have the source code to see what's going on. So they actually will very likely, as the first point of contact, call in the development engineer. So there's a chance that, these missions are long, right? How long is it going to take us to get from Earth to Europa? I think it's 5.5 years, almost 6 years. There's a chance that maybe 7 years from now, somebody is going to call you up and say, hey, Michelle, do you remember what was going on with the time module? And we just saw this happen and it wasn't supposed to. I don't remember what I did like 2 weeks ago, let alone 2 years ago, right? And that brings up a really important point to program, which is document your code, write really good comments. It's not the fun part of programming, but it's super important because what's really cool and really scary about this software that we're working on is that it lives on for decades, right? We hope that Europa will have a lifespan of 10 years, but hey, it would be great if it just kept going. We take it, right? And so your code is going to be looked at and read by many people for many years. The more you comment, the better it will be for them and for you when you go back 5 years from now and read it and are trying to figure out what's going on. And another reason that's really important is because you can use the same code or the same concepts from project to project. So much of what we're doing on Europa Clipper has been inherited from Mars, Curiosity and Perseverance, etc. And we're really fortunate that people left really good comments and really good documentation.
Thank you.
Great. Okay. So I kind of gave and we already sort of started talking about what we do, what I do, and in-flight software integration and test. But I'm going to jump back a little bit to topic I wanted to make sure I cover, which is when things don't go the way you wanted them to. So with Europa Clipper, you know, what we're going to be doing, what the mission will be doing is launching, and it'll have that, as I mentioned, 6 years of time before it actually gets to Jupiter and starts flying by Europa, and then it'll be flying around out there for I think 4 years is, I think something like that is the expected timeline. And, you know, we have all of these scenarios of when you're working on a mission, you have all these scenarios of how you expect things to go, and you plan for, you know, like I mentioned, the fault protection. You plan for some things to go wrong, and you have your backup plan. But sometimes everything goes wrong and your mission fails. That's just the reality of the situation. I had this experience when I was in college. So there's a project I worked on which was a CubeSat project. So a CubeSat or Cube satellite is basically a small, I think it's 10 centimeter cubed satellite, and they really have gained popularity in the last couple of years. There's a lot of student clubs, especially at universities, and I'm sure even high schools now, that work on this. But it's pretty much this concept of, you know, hey, satellites don't have to be this huge thing that only like big companies with a lot of money make. A lot of students, you know, if we say we're going to just do something small, actually have a lot of the tools at their disposal to be able to make satellites, to make something that goes to space. And when I was in college, this was like kind of a particularly up and coming topic. So we, in college, for one of our group projects, were able to pick from a list of things. We decided to make a cube satellite, and it was, you know, about as DIY as you can get. We got like scrap metal from this other lab. We just were walking around. We're like, oh, there's metal. That'll be perfect. We had a $300 budget, I think. And so we got like a little Raspberry Pi. We got a couple of sensors that we threw onto it. One of the guys on my team was really good with, I think it's called like a CNC machine. So he etched a little UW Husky on one of the faces, and we were like, thought that was the coolest thing ever. And we were so excited. We decided that the way we were going to launch this Cube satellite would be using a weather balloon, so a helium weather balloon. We drove out from Seattle to Moses Lake at 4 a.m. on a Saturday, and we had a helium tank in the car. We were able to get a budget increase to get the helium. I remember that. And we got there at this park. We basically had a really simple setup ultimately, which is our Cube satellite that we had created with the computer being our little Raspberry Pi. We had a parachute that we ordered from, I think, Amazon. And we, had done our calculations that this is about how much helium we'll need to put in this balloon for it to like officially hit space, if this is how much our CubeSat weighed and all of that. And we had a couple of sensors on board. So it was a very fun, hands-on project. It was a team of 4 of us. And we were so excited, and we tested everything out right before we actually launched, and by launched, I mean just let go of our balloon. We tested all of our systems that we were getting information from our satellite back to our computer. So things were looking good. And then, we let go, and we're waiting for the computer to get our signal, and we see it flying away, and there's nothing. Radio silence, absolutely nothing. And our Cube satellite, as I mentioned, we launched from this remote kind of area in Moses Lake. And our satellite was wrapped in this bright pink foam box. And we made it bright pink in the off chance that it landed in a field or something, that maybe somebody would notice it and call us. And the next 3 days, we waited for that phone call that, maybe a farmer found our satellite after it fell back down. Nothing. And that was really, really disappointing, because you put hours and hours of work into, this, in our case, it felt like blood, sweat, and tears. And it wasn't just a minor failure, it was a complete failure. There was no data collected. We couldn't even find our satellite. We drove around the area for a while, but those things, it's going to go far away potentially. And I was super, super, super disappointed. I was really disappointed. The next week, we went back to school, and we told our advisor, who was one of the professors, he was the advisor for our project. And he had a really interesting response. He said, I want you to write me a paper on everything you learned from your Cube satellite. And I was like, well, we don't have any data. We didn't learn anything. I have no measurements, right? And, especially in STEM, right, you think of, measurements, and that's how you get information, and that's how you like make conclusions, right? And he said, I don't want, and he said, no, not conclusions, not measurements. I want you to tell me everything you learned from your CUBE satellite. And so I was like, well, I guess we learned how to use that CNC machine. And I guess I learned about that Raspberry Pi and how to use these sensors. And so I started writing this thing down. And I realized in a project that had quote unquote failed, I learned a lot of things. So I think it's something really humbling when you have a failure to step back and realize that you probably learned a lot more than you realized. Certainly we learned a lot from trying to figure out what was going on. We learned, the whole map of Moses Lake, basically. And we also learned like debugging this radio signal that we were trying to fix. And there's a lot of value to the projects that fail. And I say all of this because it's almost inevitable that eventually you're going to work on something that's going to fail. And hopefully it won't be this Roads on Icy Worlds project you're working on. And hopefully it won't be on something that, you spent too much time or money, but it might be. And that's okay, because you can still come out with a really good plan for your next project, because that's ultimately what, science and engineering is all about. You have your orbiter that you learn from, and then you go and make the lander, right, et cetera. So you'll still be adding to hopefully your path. I think I saw some questions coming in. Do you start to learn programming in high school, or did you start programming in high school? No, I actually didn't program in high school at all. I didn't know what programming was, like that word, and I don't think we had that subject in my school when I was there. I really started programming in college. And don't forget about wing it. Like, oh, I actually read this paper. Yes, there's a lot of value, as I think probably many of your speakers and many of your topics have talked about, for things that don't go as planned. So with that, I think this would be another time to take a break and see if there's any questions that you have about anything so far. What's your proudest moment in coding something? Ooh, that's a really fun one. So when I was working at the wind tunnel, there was a really unique project. So typically when we had wind tunnel projects, there's like a test section, basically a room, where the model that you're testing sits. And it sits on a balance, or like a scale. So it's really similar to the scale in concept to like what you stand on when you go to the doctor's office and they take your weight, right? Like that's them measuring a force, really. So it's really similar to that, except it's for a aircraft model to sit on, and it's going to measure not just the weight, but a bunch of forces and moments. So typically that's how the wind tunnel is used. You turn the wind on, you get all of this like force and moment data on this model. We had a customer, it was actually a research project that was funded through NASA, come in, and they wanted to see not the forces and moments. They wanted to put a big wing in the wind tunnel, and they wanted to see the deflection of the flaps at different wind speeds. They wanted like the measurement in like centimeters of how much this wing deflects, because it was a very special wing made of these new materials and this new design, et cetera. So we basically had to figure out a way to collect that information. And this idea that ended up happening, which I think is brilliant, is if you've seen like CGI, is that what it's called, characters in like movies and stuff, like when you have like some animated character in like a person movie, in a otherwise real people movie, it will be typically what they do is that there's like an actor, and they have these little like silver dot looking things on them, and they go in front of a green screen and they move their hands like crazy, and that's them acting out, and then they take that and translate it into this animated character, and they use all the movements of the real actor. We used that same technology, so we ordered that system and decided to put it on this wing that we were going to be testing. But the really unique challenge with that is, as soon as you start putting these little globes, these little silver, reflective globes all over the wing, it's going to change your physical data that you're collecting, right? Like it's actually changing that information that they're collecting. And we needed to basically account for that. And so what the team ended up doing was we ended up working with a couple of students and professor to account for like how that's changing the data that ultimately the customer was looking for. And then I basically helped to translate that into our MATLAB post-processing code. And the reason I'm super proud of that is because it truly was an example of like how much of engineering is a team sport and how coding is not something that exists in a vacuum. You know, you're typically coding for the purpose of solving a problem. And for me, those interesting problems are in the aerospace domain. And so it was like a perfect opportunity to work with experts in these various like physics domains and aerodynamics domain, and then taking my skill, which was the coding part, and helping to answer that physics question in this particular case. So I was really proud of that. And because it was one of kind of the first super creative things I got to do in programming. Any other questions? Good questions, by the way, so far. These are fun. Oh, someone wrote, "That's so cool and clever." Thank you. That's very nice.
I'll ask another question. Unless do you have more to present? Because I'll ask.
No,
I'm curious about.
Go for it.
So, what is your like typical day like? I think a lot of students are interested. You know, like how much time are you meeting, or like are you sitting at a computer a lot? Are you interfacing with people other ways? Yeah.
Great question. I would say that my typical day is probably a lot of programming. There's a lot of sitting at the computer solitary for sure, but probably not the whole day. So typically how our team works is that once a week we start the morning with like a team meeting, and you sort of see where the project is at. You see how much progress everyone has made. You know, in a lot of like tech companies, for example, you might have these types of meetings every day, like the stand-up 5-minute meetings. But because the timeline of our projects are so long, it doesn't make sense to do that every single day. So our, you know, our checkup like that is typically once a week. And then I will typically spend like the first half of the day, first like 4 hours or so, or after that meeting, if it's a Monday, just sitting at my station programming. So what I do is basically automate tests for the modules that I'm testing. So going back to our little, you know, example, there's the, well, this is an example. This is actually the real scenario. There's basically a developer who's working on, you know, instrument software, and I will like create a test suite that will test all of his modules. I also do like the fault protection and timekeeping and a few things like that. So I'll spend like 4 hours basically working on my tests, and that's pretty much straight like programming. That's all in Python primarily, and using those in-house frameworks that we talked about. And then probably an hour or so will then be, okay, you did your 4 hours of testing, you probably found bugs, right? That's the point of your job, is to find the issues. So I'll probably spend an hour or two maximum a day finding the people that I need to figure out what's the problem. And this sort of goes back to a really early on question we had, which is, you know, what's like some clubs or things you did that might have helped in high school? And I mentioned like some of my public speaking and clubs. A lot of the type of software engineering I do is talking to a software developer and saying like, hey, I tried your code out and it didn't quite work as I expected. Can you tell me what's going on? And, you know, reading their code, etc. And then, you know, it might work exactly the way the flight software developer intended it to work. So the next question then is like, okay, they implemented it correctly, assuming it's supposed to do A. Was it actually supposed to do A, or was it supposed to do B? Because there is, you know, if there's one, if something is written down, right? Like when a software developer gets a piece of paper that says, you know, create a program that does XYZ, there's 500 ways to interpret XYZ. And we're sort of sitting as integration testers, we're sitting at that interface and making sure everybody thinks XYZ means the same thing. And interfaces where people hand something off to someone else to implement or to test or to, just read or check out, interfaces are where you have problems. That's just a fundamental truth, because that's where it goes from someone's perspective to someone else's perspective. And we are testing those interfaces. We're making sure that everything integrates together cohesively. So part of our job is talking to the people who are implementing everything on one side of the interface and implementing things on the other side of the interface, and making sure those two things meet as planned or as desired. And it can be something as small as, oh, the developer actually did have a bug, and we agree that they'll just fix that, and we don't even have to get a different engineer involved. But a lot of times you have to go up the chain, and you have to go. So in our case, it starts with the avionics engineer who is responsible for that area, and we'll say, okay, here's what happened. Can you clarify what this means? And usually they'll be able to clarify, and we fix the code, or it might be my test. Oh no, your test was testing the wrong thing. It's fine. Sometimes they don't know, and you work your way up. So flight software, where I'm working, is sort of at the lowest, most like granular detail level. But at the end of the day, what do we care about? Mission objective, right? So you work your way up the chain, and ultimately, at every level of detail, there's sort of engineers who are translating your highest level mission objectives into what needs to be done at that level. And when something goes wrong at the lowest level, like software, you then work your way back up until you fix the kink in that chain, so to speak. And that's actually the last topic I was going to talk about, was basically exactly that, which is what I actually do every day, and what does it mean to integration test. So that's at a high level what it means to be an integration tester, and that's the concept of what we're doing. And the big part of that is that Europa Clipper is in development. It's like a living project right now. It's constantly changing. So the programming that comes into that, there's the programming of the actual flight software. And then there's programming to test it, because basically you've got, a team of 20 plus developers that are changing things all over. And you think something you're doing here doesn't matter at all to somebody working over here, like, oh, why would working on this instrument manager matter at all to propulsion? Well, it turns out it does. And if you press this button on instrument A, your rocket engine fires badly and something crazy happens. And that's what we're testing, and we have to make sure that no matter what change happens, the software still continues to work as we expect it to. So we automate all of our testing. We basically have these test suites that run every single night, and they take hours and hours and hours to run. And we run them all overnight, so that every single night we have a snapshot of, here's everything that changed that day. Here's the test that ran, and this test had been running fine and has not changed for 10 days. And then all of a sudden you have a failure. What changed that day? What could have caused this failure? And it might be something in your area. It might have been like, oh, you were testing the clock and they changed the code of the clock and it was, a bad change. Or it might have been like, oh, they didn't even touch the clock code at all. They touched something else and it somehow is impacting you. And then you get to do that fun dance again of going and finding the right engineers, going and finding the right developers. And it's often other software engineers, but it's also often, people in the domain. So the domain experts that you'll have to bring in. So it's a really fun and collaborative process. And I think if there's one other kind of big thing I can leave you with regards to programming specifically, is that, I think I said before, you don't code in a vacuum. You're writing code to do something ultimately. And if you can find what that something is that you're really interested in and that you're really excited about, it'll make it more fun when you inevitably run into your bugs and run into those problems that keep you up at 5 a.m. and you need to go step away from your computer and take a break, like I said. But that's what's going to keep you excited about the project you're working on, because you'll be able to see a really, really fun application. And that's why I love working on Europa Clipper, because, I'm certainly not a scientist. I'm certainly not someone who's like an astrobiology expert, but I think it's so cool that we're going. And I'm sure you've heard from like the scientists in previous talks, some of the amazing discoveries that they're trying to make, some of the amazing like science information they're trying to capture, both about Europa and beyond, really, and about our solar system at large. And I think it's so cool that, like, you know, my little skill here can add to that. And that's true of any skill you have, I think, whether it's STEM or not. If you find a way to apply it to something that you just think is really exciting and fun, like there's no better way to spend your career, I think. And with that, we'll leave the last few minutes to any final questions.
Okay, go ahead and put any questions in the chat. You guys can also ask questions through the video if you like. I love that point because I think a lot of people actually are surprised at how much they enjoy programming once they learn how to do it.
Oh yeah.
And I'm a scientist that also programs, and from that perspective, like what I find satisfying about it is that you actually like have a thing that you can accomplish that you like fully finished, which I'm sure like if you talk to the Clipper scientist, right, they've probably been working on this one problem for who knows how many years, and like, you know, will we ever really know the answer? Probably not. We might get like the error bars a little smaller. So there's something very satisfying about programming. Yeah, and it, like, you know, when it's wrong, like it's wrong, but then at some point it works, and then you're like,
when it's finally right, it's worth all of the trouble.
Yes. So some of the students out there, you might find if you haven't tried programming yet, there's always a learning curve, a barrier, and you feel like you've never done it before and maybe you can't figure it out. But once you do, you might actually find out you really like it.
Absolutely. And there's so many resources out there nowadays, online, like so many free resources. And there's also a lot of like community organizations now. So if you're nervous about stepping into like the computer science world for whatever reason, you know, there's a big thing for me particularly was I never knew the topic, and I certainly never saw people that looked like me in that type of role, so to speak. And there's a lot of community outreach now that's done to alleviate that exact problem. You know, there's like Girl Develop It and Girls Who Code and various affinity groups around the topic of STEM at large. And then especially, I think, for coding and programming, there's been a lot of effort. So definitely reach out. And I'm, again, a big proponent of like making you know, those mentoring relationships. And it can be super awkward, but reach out to people that are you know, that you hear at talks or wherever you go, because they typically, certainly at JPL, my experience has been, and I think just at large in my career, my experience has been people want to help. And the best part is, you guys, the best part is, especially when you're a student, they expect you to know nothing, right? So if you're asking 5,000 questions, no one's gonna bat an eye. If you're like me and you've been working a few years and you ask some questions, someone might be like, why does she still not know this? And certainly 10 years from now, they might be like, she should really have picked up on this by now. But as a student, go crazy. Ask every question. There's no reason to think that you should already know something, because nobody expects that from you. Mm-hmm. And I would say take advantage of that while you can. And jokes aside, definitely continue to ask questions throughout your career. I think it's a really, really fantastic part of the culture in aerospace, that it is such a big topic. And really, you know, scientists and engineers in general, it's impossible to know everything, even about a really specialized topic, you know, unless you happen to be the person who did the PhD on that very topic. There's no way you'll know everything. So ask those questions, because people expect that. And that's also how we're going to have the knowledge transfer from, you know, the people who do know to the people who don't. Because if you don't ask the questions, no one's going to answer them.
And on that, your PhD, there's someone that's been studying it for like 20 more years than you. So you're still not an expert.
Exactly. And I was going to say, on that note, I will put my contact information in the chat before I go. So if there's any questions you have, you can feel free to reach out to me after this if you don't want to ask right now, whether it's about JPL and technical questions, or if you just want to talk about, like, you know, career stuff, feel free to reach out, because, you know, I'm going to practice what I preach and try to be a good mentor to anybody out there who's looking for one.
Thank you. That is very generous of you. Now I'm like, I wish I would have made my undergraduates watch this too. They would definitely be emailing you. But yes. Does anybody else have questions that are online? Now or never, guys. This is your chance.